Imagine a place in the cosmos where gravity is so powerful, so absolutely dominant, that nothing can escape its grasp. Not a spaceship, not a planet, not even light itself. The fastest thing in the universe. This isn't science fiction. This is a black hole. It's a region of space-time that has collapsed under its own immense weight, creating a gravitational well so deep that the rules of our everyday reality break down. Think of it as the universe's ultimate trapdoor. Once you cross its threshold, there is no turning back. The very fabric of space and time funnels you toward a single, infinitesimally small point. It's a concept that stretches our imagination to its absolute limits. The allure of black holes lies in their profound mystery. They are the ghosts of the cosmos, invisible by their very nature. We can't see them directly because they swallow all light that gets too close. The story of the black hole begins long before we had the telescopes to find one. It starts not with a discovery, but with a question. Back in 1783, a brilliant English thinker named John Michell had a radical thought. He knew about gravity, thanks to Isaac Newton. He also knew that light behaved like particles with a finite speed. So he asked, could an object be so massive that its escape velocity exceeded the speed of light? It was a stunning piece of reasoning. He called them dark stars. Any light would be pulled back, making them invisible. For over a century, this stayed a mathematical curiosity, tucked into footnotes. Then, in the early 20th century, a patent clerk named Albert Einstein rewrote gravity. In 1915, he published General Relativity. Gravity is not a force, but curvature of space-time. Massive objects bend space-time, and other objects follow those curves, like a marble rolling around a bowling ball on a trampoline. Einstein's equations hid a bizarre prediction he barely accepted. A few months later, Carl Schwarzschild found a solution to those equations. His math showed squeezing huge mass into tiny space produces a singularity, infinite density. That singularity is surrounded by a boundary, a point of no return, the event horizon. Schwarzschild had described the modern black hole, but the idea was dismissed for decades. The term black hole wasn't coined until the 1960s by John Wheeler. Work by J. Robert Oppenheimer and Subrahmanyan Chandrasekhar showed how such objects could actually form. Not every star gets to become a black hole. In the cosmic lottery of stellar death, only the true heavyweights win this particular prize. For a star like our Sun, the end is a much more graceful affair. When it exhausts its nuclear fuel in a few billion years, it won't collapse violently. Instead, it will puff up into a red giant. It will shed its outer layers to create a beautiful planetary nebula, and it will leave behind its cooling, dense core, a white dwarf about the size of Earth. Stars a bit more massive than our Sun go out with a bigger bang, a supernova explosion. They leave behind an incredibly dense object called a neutron star. Matter there is so compressed that a teaspoon of it would weigh billions of tons. But for the real giants of the cosmos, stars born with more than 20 to 25 times the mass of our Sun, a far more dramatic fate awaits. These colossal stars live fast and die young, burning through their fuel at a furious rate. For millions of years, outward pressure from nuclear fusion battles the inward crush of gravity. It's a titanic struggle. Eventually, the fuel runs out. The fusion stops. The outward pressure vanishes, and gravity wins. It wins definitively and catastrophically. The star's core implodes in a fraction of a second, collapsing under its own staggering weight. The outer layers crash down onto the imploding core. Then they rebound in a spectacular explosion, a supernova. The blast can briefly outshine its entire galaxy. It scatters heavy elements forged in the star's heart across the cosmos. These elements go on to form planets, and even us. But while the outer layers are blasted into space, the core keeps collapsing. In that moment, a black hole is born. To understand a black hole, you have to dissect it, piece by piece. But this isn't matter, in the traditional sense. It's warped space-time. Its anatomy is defined by gravity itself. At the very heart is the singularity. The collapsed star's mass is crushed into a point, with zero volume and infinite density. Here, our laws of physics, including general relativity, break down. We can't describe the singularity. because space and time cease to exist there. It's the ultimate unknown. Surrounding it is the event horizon, not a surface you can touch, but an invisible, one-way boundary, the point of no return. Its size scales with mass. Anything that crosses it, a particle of light, a giant star, is trapped forever. Escape would require faster-than-light travel. Impossible. Most black holes aren't isolated, they are messy eaters. It spirals inward into a vast rotating accretion disk. Sometimes a feeding black hole also spits matter out. These are relativistic jets. So, what would you actually see if you were looking at a black hole from a safe distance? Well, it's a tricky question. The black hole itself is perfectly black. It emits no light of its own. But that doesn't mean its location is empty. The real spectacle comes from the chaos around it. The most striking feature, the intensely bright accretion disk, a swirling vortex, superheated gas, dust, a glowing flattened donut of plasma. The inner parts shine more brightly. They emit at higher energies than the outer parts. A cosmic whirlpool of light spiraling inward. That light looks strange, distorted by extreme gravity. The side spinning toward you appears brighter and bluer. The side spinning away looks dimmer and redder. You'd even see light from the back of the disk. Gravity bends the path of that light, like a powerful lens. It lifts light over the top and under the bottom, letting you see the whole disk warped into a halo. At the center, the black hole's shadow, the visual signature of the event horizon, a circular region of pure blackness. The shadow appears larger than the horizon itself. This is what the Event Horizon Telescope imaged at M87. Not the black hole directly, but its shadow outlined by glowing infalling matter. The star field is distorted, a funhouse mirror effect. Let's imagine you've decided to take the ultimate plunge and fall into a stellar mass black hole. What would you experience on your journey to the singularity? Let's assume you're falling feet first. As you get closer, gravity increases dramatically. But it wouldn't pull on your body evenly. The pull on your feet, being closer, is immensely stronger than the pull on your head. That difference is a tidal force. It would begin to stretch you, gently at first, then with rapidly growing intensity. This process has a memorable, if grim, name: spaghettification. The tidal forces pull you apart, elongating you along the fall and compressing you from the sides. You'd be stretched long and thin, like spaghetti. The process is relentless. Your bones would snap. Your tissues would tear. Eventually your body rips into a stream of atoms. That atom stream spirals down toward the event horizon. A final, thin whisper of what was once human. Not pleasant, but inevitable when meeting extreme gravity. Now, let's rewind. What if you weren't the one falling in? What if you were watching your brave, or maybe foolish friend, take the plunge? Observing from a safe distance in your spaceship. From your perspective, the story would be completely different. As your friend falls toward the black hole, you would see their clock begin to slow down. You would see their biological processes begin to slow down. This is gravitational time dilation, predicted by Einstein's general relativity. The stronger the gravity, the slower time flows. As they approach the intense gravity near the event horizon, their time ticks much more slowly compared to yours. You would see your friend's descent get slower and slower. You'd watch them approach the event horizon, but they'd never seem to actually reach it. Their image would appear to freeze just outside the boundary, getting dimmer and redder over time. The light they emit must struggle against the black hole's gravity to reach you. That struggle steals energy from the light, shifting it to longer, redder wavelengths, gravitational redshift. Eventually, the light is redshifted beyond visible, infrared, radio waves, undetectable. From your point of view, your friend is frozen in time at the edge of the black hole, slowly fading away over an infinite amount of time. You would never, ever see them cross the event horizon. Black holes are far more than just cosmic oddities or celestial vacuum cleaners. They are fundamental architects of the universe, shaping the cosmos on the grandest of scales. At the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, millions or even billions of times the mass of our Sun. Our galaxy's central black hole, Sagittarius A, weighs about 4 million solar masses and acts as a gravitational anchor around which our entire galaxy revolves. These behemoths grew with their galaxies, their evolution deeply intertwined. These supermassive black holes are not passive residents. They are active engines that regulate galactic growth. As they feed on surrounding gas and dust, their accretion disks can blaze with the light of 1 trillion suns, quasars. Intense energy and radiation can heat up and blow away the gas in the surrounding galaxy. That can shut down star formation, effectively sterilizing the galaxy and limiting how large it can grow. Black holes act as cosmic thermostats, controlling star formation on a galactic scale. This effect, known as gravitational lensing, lets us use black holes as natural telescopes. They magnify and distort background galaxies, revealing the early universe. They help map matter, visible and dark, across the cosmos. When two black holes merge, they send ripples through spacetime, gravitational waves. Predicted by Einstein a century ago and first detected in 2015, these waves travel at light speed. Detecting them lets us hear violent cosmic events. So, let's bring it all back home. What is the big picture here? A black hole is what you get when you crush an enormous amount of matter into an impossibly small space. It's the ghost of a massive star, a region of the universe where gravity is the undisputed champion. Its pull is so strong that once you cross its event horizon, its point of no return, you can never leave. Not even light can escape. It's a one-way street leading to a singularity. We can't see them directly, but we know they're there. We see their handiwork all across the universe. Brilliant swirling accretion disks of superheated gas, powerful jets launched across galaxies, distorted light from distant stars bent by gravity. And now we've even seen a black hole shadow, a dark silhouette against a ring of fire. If you fell in, your experience would depend on who was watching. You would be stretched into spaghetti by tidal forces on a short journey inward. From afar, observers would see you slow down, redshift, freeze at the edge, and fade away over an eternity. This paradox shows that near extreme gravity, time is not absolute. It's a cosmic lesson that the universe is stranger than we imagine.